we're gonna do examples on all those, but I need to show most of the equations and recapping all the equations overall. Now, we discussed, I guess, mass, we discussed mole fraction, we discussed pressures, but what about other properties like CPs, CVs, energies, entropy? Well, since they are, in a sense, extensive properties, and we're not reacting at this stage, what we could just do is have an additive-based process. So let's outline a law for it. So properties of non-reacting ideal gas mixtures so species that are not interacting the extensive properties simply additive or addition of the contributions. So let's take an example and say, well, internal energy. E for internal energy is going to equal to the summation of I1 to N of each individual internal energy of my species. So the sum is going to equal to, this is total internal energy in terms of my mass multiplied by the internal energy, the lowercase internal energy, so I can say it's multiplied by mass multiplied by the lowercase internal energy. Now, if I say specific internal energy, I'm going to say E divided by M total. And that's going to equal to lowercase e total. And that's going to equal to the same principle. So sorry, 1, summation of I equals 1 to M EI MI over M total. Let me write some units here. So, bless you. This will be in terms of your kilojoule over kilograms. The mass specific will be kilojoules per kilograms. And this is kilograms, and this is kilograms. So, units check out. So if I want to write a generic formula for this, just a general form for this equation, E total is equal to the sum. What is MI over M total?
Yes.
Y I. Did they use YM? Is that I confusing you? You used N and M for subscripts? Okay. I just represents the number of species. You might have carbon, hydrogen, oxygen, and we're going to do an example on it. So let me get to that example. We're going to use all the equations. I equals 1 to n, and we just said that this is my mass fraction of that species multiplied by YE. So that's the general form of my equation. And I could write the same total is equal to sum y equals 1 mass fraction. Can I? Do the units check out? Right? The units are, this is in kilojoules per kilogram, this is kilojoules per kilogram. This is kilograms per kilogram. So if I go and say, well, I'm going to multiply it by the mole fraction. Can I do that?
Yeah.
Yeah, it's a percentage. That's what it is. So yes, I can do that. That's how you can actually use both without an issue. In most calculations, you're not, actually all calculations, you're not going to have an issue if you know, if you're used to using mole fractions or mass fractions. But you'll find it easier when we're doing chemical reactions to use mole fractions. That's why you will sort of sometimes prefer, it's easier to just do the counts and not have to worry about the kilograms. But it's harder for engineers because engineers want to target a specific unit. And that's why we want to be precise. That's the problem. Versus chemists that will say, well, I have this much moles and I'll worry about the mass or the kilograms or grams of that later on and convert it into that later on, because in the end it does have a mass to it. Okay, so that same principle, we could apply it to, so we said mass fraction, so if I say E is equal to if I'm doing the summation right here, so let me write this equation right here as well. It will be E total multiplied by M total. So you have it right here, but I just want to write it. And the same principle, if I already know the total here, then I can just say it's equal to E total, or E total bar, and I'll show you the bar. Let's see this. Multiplied by N total. Well, that means I have to convert that E total to have the same balance as my M total, mass total. So how do I get E total? It's simply equal to the summation of each individual mole fraction multiplied by my energy for that specific species equals 1. So this, however, over bar is kilograms per kilomoles. And this is kilograms, or sorry, kilojoules per kilomole. So let me write the other one again. Where do we write? We're writing here. Let me write them side by side. Total is equal to the summation of N, I equals 1, the individual mass fraction multiplied by E of that species. So this will be kilojoules per kilograms. This is kilojoules per kilograms. So this is where it's very, very important to differentiate between your units. So let's take it as a rule to put this over bar for moles. So you can see one of the issues that you're having there. You can keep it in terms of actual kilojoules per kilomole, but you want to differentiate between them if you're going to actually keep it in terms of kilojoules per kilomole. So be very wary of your units. Okay? So And probably it would be best to differentiate them from now on. Have a overbar over your mole fraction versus the mass fraction, so you don't mix them up. You know that this is always in terms of mole fraction or mass fraction. If you're going to cross between them, but if you say, I'm just going to do it in mass fraction, now, you're not going to have a choice in homework number 2 because I'm having you do both. But later on, when you're doing your engine calculations, you're going to be choosing which one you want to choose. So just, if you're going to use moles, continue using moles. And if you're going to use mass, continue using mass. Then you're fine. But just differentiate your nomenclature so you don't get confused. Okay? So other properties, well, if the same as the energy, we could say that H total, I'm going to list them under this, H total is equal to the summation of I equals N, Xi, Hi. So here's another issue again. Well, what units am I keeping this at? So let's keep this over bar, and let's do the other side and say it's H total equals the summation of N equals 1, the mass fraction multiplied by Hi. Same thing with entropy. It's equal to the summation of I equals 1 and, oh, sorry. Thank you. So enthalpy, entropy, and this is in terms of moles, this is in terms of mass, entropy of each individual species versus entropy of Ni multiplied by mass fraction Si. And the same thing I could apply for the specific heats. I could say Cv total is equal to the summation of each individual I multiplied by Cv of I equals 1 to N. And now let's keep the over bar so we can differentiate between both. And I'm listing them on the same page here so you have them right next to each other. It's equal to summation of I equals 1 to N Yi Cv I. And the same thing with Cp. Total is equal to the summation of I equals 1 Xi Cp I versus Cp of the summation 1 to N Yi Cp of I. And the list keeps going on. So, essentially, as I mentioned, it's just simply a summation multiplied by the mass fraction or mole fraction, depending on what work frame you're actually choosing. But as long as you can get your mole fraction or mass fraction, you can just compute the different enthalpies that you have. Now, why is this important? Because once you go to reacting systems in the end, think of how we got Q. How do we get Q for the combustor? We just said, bless you, we said it's the difference in enthalpy, right? Mass multiplied by difference in enthalpy. Well, in the combustor problem that we just did last class was, we just assumed one single species. We didn't really differentiate, know that I have multiple species or multiple gases that are going through. So in the end, here you're going to have to take all these mixtures and put them together and compute each individual enthalpy. And we're going to go through examples of this. All right, so before we do the example, just final touches on changes in extensive properties, which we just did. Well, if I have E2 minus E1 is going to equal to what we wrote before, the summation of I1 of mass fraction of E2 minus the summation of I1. I multiplied by the I of the first state. The whole thing multiplied by M total. So meaning, by taking a delta in energy, which we're going to have to do quite a bit, we're going from one state to another, through, let's say through the combustor. Think of this as enthalpy. The rate of change from 2 to 1, like we just did in the last problem, that's the same principle. Now I have to bookkeep each species, but the mass fraction doesn't change. So what's going to change, this is non-reacting, very important, because later on it's going to be reacting and some of these are going to change. But non-reacting, if I take this together, well, it's just a mass fraction is a mass fraction. I just take two gases, mix them together, it's still the same mass fraction for each gases, as long as they're not reacting. Let's assume you have a container, as said, with hydrogen and oxygen. You move that barrier with no catalyst to react, although they're supposed to be a reacting mixture, they're not going to react. You pretty much just got hydrogen and oxygen just diffused together. But they mixed energies. So in reality, they were, and for each species, they were at a certain state. They were starting at a specific state, and then they end up at a second state. But I want to know, how does that change? What if one is hotter than the other? And we're going to do an example on it. But by outlining this equation, we want to determine what is the variable, and in this case, the mass fraction is the same. So what I could write as a general form for this is M total, the total mass, multiplied by the summation of the mass fraction, that's nominally constant, and multiplied by the delta of that individual species. How that individual species is changing, its energy of it. And the same principle I can apply for the conservations. So species conservation for 1D, like we read before, steady state, my conservation is simply the total amount of mass. So if I have a sum of mass of that species in is equal to the sum of out, assuming again steady state one-dimensional, of m dot of that species that is going out. It's conserved. I know it's too many equations, but let's do an example. I think it'll be clearer once we do the example. Any questions thus far? Let's do an example, and then you will see some of these equations being applied. We're going to do a big example with leveraging everything you just did. So, example. So, mixing of two separated gases I have a container that is insulated, so I don't want any heat losses outside of